Our next speaker is Dr. Susanne Benz. So Dr. Susanne Benz is a post fellow at Dalhousie University. She focused on studying climate change in the subsurface and future scenarios for geothermal pollution, groundwater quality, and groundwater groundwater dependent ecosystems. Today, her topic is heat recycling in the shallow surface. So, Dr. Benz, please.
Thank you very much for the invitation. Thank you very much for giving me the opportunity to present my research today. I want to talk to you today about the geo-resource heat. So where can we find it? How much of it is there? And also, can we use it sustainably? This topic has basically been part of my research since forever, since I started my PhD. And accordingly, there are quite a lot of universities kind of put on top of this first slide. I want to also highlight it, of course, this is not just my work. I couldn't do any of this without my awesome colleagues. I want to specifically highlight Peter Bayer and Philip Bloom, who years ago used to be my PhD supervisor, but are still to this day dear friends and colleagues, and together we kind of focus on the topic of heat recycling in the shallow subsurface. I said before that I want to talk to you about heat as a resource. So the first thing we need to do is figure out where actually is heat. And the best thing to do so is just taking a thermal image, in this case a thermal image of Nanjing, and figuring out where is it hot. Here you're seeing in the bluish tones, this is more like the 20 degrees Celsius, and in the reddish tones, it's at 23 degrees Celsius. And you will notice the city is notably warmer than its rural background. Because what you are seeing here is that Nanjing is a prime example of what we call is an urban heat island. So the city is more warm than its rural surrounding. We can quantify this phenomenon, for example, by using what is called temperature anomalies. This is a super simple equation. It simply takes the temperature at one point, this is the T here in this equation, and then subtracts the rural median background temperature. In this case, we're doing this with satellite temperatures, but you can also do it with air temperatures, or what we're going to get to later, subsurface and groundwater temperatures. In the picture right above here, you're again seeing Nanjing, just showing how much warmer it is than a rural surrounding. And in the graph here, you're seeing the same thing for daytime along the x-axis and nighttime along the y-axis. And you will notice, hey, Nanjing is about 4 degrees warmer at daytime than its surrounding areas during the annual mean, which would be this black dot right here. We have run this analysis not just for Nanjing, but for every single pixel of the globe, which in total is about 200 million pixels, which allows us to figure out how many people do actually live in urban heat islands. And we find that 75% of the urban population experience summer surface urban heat islands during daytime and nighttime. I haven't checked what the weather is like wherever you are at the moment. In the US, we have a heat wave going on at the moment. So these people that experience urban warming during daytime and nighttime are exposed to additional temperatures, and it's just unbearably hot. Which brings me to my next slide, which I just want to tell you a little bit why we should actually care about heat above ground specifically, because here it is a dire problem. Heat is detrimental to our health. What you're seeing here is not a study from me, but it's like an awesome study a couple of years ago that linked heat waves to deaths. And we find that hot temperatures, particularly hot temperatures combined with humidity, lead to a risk of deadly heat. So people keep dying because of this heat, which is not great. Also, if you think, hey, I'm young, I don't care, I won't die, well, your test scores will likely go worse with heat, because heat is detrimental not just to your health, but also your productivity. Below here is the study of one of my colleagues at UC San Diego, and you will notice the hotter it is, the worse children did in test scores, in math in this case, but also in reading and everything. So heat at the surface is very detrimental to our health, very detrimental to our well-being, and it is very, very much located in cities where all of us live. So heat at the surface is a serious issue. However, this urban heat island phenomenon is three-dimensional. It's not just at the surface, but we can also find it underground, which is what you're seeing here at the example of 3 German cities. We have Berlin, Cologne, and then Karlsruhe 2 times for 2 different years. In this 4 plots above here, these are groundwater temperatures. So we went in the field, measured groundwater temperatures at about 10 meters depth. Below here, you see the compared land surface temperature. These are satellite-derived temperatures of Earth. And you will notice both of these plots do show that city centers are a lot warmer. So urban heat in the subsurface and at the surface are correlated. And in fact, we find that urban heat in the subsurface is simply the waste heat of our surface urban heat islands. However, when we subtract those two, you will also notice that urban heat in the underground is even hotter than the surface. And we find quite a few places where temperatures are pretty extreme. So here, groundwater temperatures are like 20 degrees Celsius hot, 17 degrees Celsius hot. They are very, very warm for European feelings, which is the next couple of slides that I want to show you. I want to quantify groundwater temperatures, not just in cities, but everywhere. So we want to find, we've identified some hotspots. Now I want to find where are more hotspots. Where are groundwater temperatures actually really, really hot? And I promised you we're going to get to the reciting part a little bit later and figure out why this is actually important. What you're seeing here are about 10,000 wells in all of Central Europe. These are all shallow wells, so less than 60 meters deep. And for each of them, we measured not just groundwater temperature, but we again measured this delta T, so the difference between temperatures at that place minus a rural background temperature, to again figure out how much warmer or colder that place is compared to its rural background. We've done this for all of these wells, and kind of for some of those, we had land surface temperature available, so we can actually compare them to the surface level. So what you are seeing here is a comparison between surface temperature anomalies, this would be here along the x-axis, and groundwater temperature anomalies, this would be here on the y-axis. The blue dots is what I'm talking about. Red is air, we are talking about groundwater, in this case blue. So what you are seeing here is that groundwater extremes are much more extreme than atmospheric or surface level extremes. So if you think your city is hot above the surface in your living room, go 10 meters down and groundwaters will be a lot warmer than what you're seeing at the surface, because groundwater temperature extremes are more extreme than surface temperature extremes. If we kind of just want to figure out where exactly these are, we find that most of these groundwater temperature extremes are under artificial areas. So they are located under cities, they are located under streets, they are located simply under train tracks. We don't know yet. And we notice that these are on average about 1.1 Kelvin warmer than their surrounding areas. Interestingly, we find also a slight increase in temperatures about agricultural areas and groundwater temperatures. So groundwater temperature under agricultural land are just so slightly, but still noticeably warmer than their surrounding areas. Whereas forests are notably, of course, a little bit colder. You notice this probably as well. If you go in the forest, air temperature is also very colder. In the following, I want to focus on these extremes. I want to talk to you about these very, very hot groundwater temperatures in an artificial environment. And I want to talk to you about where we find those, why groundwater temperatures are so hot in these regions. This is a study that Caroline Thyssen performed in 2019, and where she looked at every single of these extreme groundwater temperature wells using the high-resolution Google Earth Engine images, Google Earth images, and just sorted those highest 5 percentiles of groundwater temperature anomalies into land utilization classes, as she called it. So this is a visual examination of all of these really hot locations and just sorting them into bins and figuring out which belongs together. She identified these 6 bins. Most of those are in cities. This kind of, I assume I kind of alluded to, was talking about urban heat and not, but most of these extreme groundwater temperatures are in city, about 1/3 of them. That doesn't mean they are not everywhere else. A lot of them are in industry parks. So this isn't in a city, this is often outside of town, but just there are industrial locations. Here your groundwater is really hot, and here your groundwater is significantly warmer, about 5 degrees warmer than the background. Waste locations also have hot groundwater. Some farming locations we mentioned before, we don't really know yet why farming warms the groundwater, but it apparently does sometimes. Automotive location, which would be things like racetracks, but also mechanics and everything. And most or the hottest groundwater temperatures we found were actually under factories. So this would be an example of this, where you have a single factory in the middle of nowhere. There's a well that measures groundwater temperature, and you find that groundwater temperatures at these locations are 7 degrees warmer than anything in the near surrounding. An example of this would actually be car parks, because we do find quite a few car parks with incredibly hot groundwater temperatures next to it. This is an example of Zurich, so Zurich in Switzerland. And what you're seeing here, that there's a well in the middle of the car park. And if you measure groundwater temperature, you get 70 degrees Celsius. Again, background temperatures are at like 11 degrees. So this is a really hot, warm spot of groundwater temperatures. And we suspect that it is in fact the building, this underground parking garage, that is heating our water. Okay, now I spent a good 10 minutes to you just telling you where hot waters are hot and kind of that they are hot and how hot they are and everything. Now it's actually time to tell you why we should care about all of this. So why should we care that not just is our city hot, also the underground is hot, also the subsurface is hot. Well, an increase in groundwater temperatures is actually associated with the decline in groundwater quality. We find that a difference, Thomas Liddell finds that a difference in temperatures of 1 Kelvin is linked to a 4% decline in oxygen saturation, the pH drop of 0.02 due to the accumulation of carbon dioxide. So warmer groundwater might mean less groundwater quality, and so, well, could be difficult. However, there's also a positive aspect to warm groundwaters, and then this is where we're really getting in this groundwater as a resource thing. Warm groundwater can also be seen as an increased geothermal potential. So I can reuse this warm temperature, and reusing is fairly necessary, because if we're looking at our energy consumption, and this is now the energy consumption of EU households, we find that really 75% of the European energy consumption, again household consumption, not industrial, but household consumption, is used for water and space heating. So most of the energy we use is used for heating our houses and heating our waters. And most of this still uses burning fossil fuels for heating materials. So not very climate conform, far from climate neutral. Hence, the introduction of heat recycling in the shallow subsurface. The idea is pretty simple. Using shallow geothermal systems to simply reuse that heat that we find in the subsurface and that is accumulated in the subsurface and all these places we were looking at before, and using it to warm our buildings, to warm our houses, to warm our bath, our water. I'm not sure how familiar all of you are with ground source heat pumps. I must admit, I am not an expert in ground source heat pumps. I am more an expert in subsurface heat. But simply put, it is a U-shaped tube that you bury underground. There's a fluid circulating that takes off the warmth of the underground, and then there's a heat pump that actually uses that heat of the underground to warm your house or your water or, well, yeah, primarily your space. This is the same technology you can use in deep boreholes. We use it really shallow, so think 10 meters, maybe even just 5 meters deep. Now, to really understand if recycling heat in the shallow subsurface is worth our time and worth our effort, and whether we should really get into it, we need to consider two things. First, we need to decide how much heat is there that we can extract. So how much heat has already accumulated in the underground due to our own waste heat, to the urban heat and all this. How much heat is there that we can extract? And then we also need to consider, well, if we just take all of that heat out, then there will be nothing left and we don't have any heat resource left. So we also need to know how much waste heat does the city lose into the subsurface each year? So how much heat input into the subsurface does an average city have each year? Answering the first question first, how much energy has already accumulated? This is actually a quite simple equation that I've put down here in like the little corner. When we know how much warmer temperatures are in location than their natural state, so again we equate this to how much warmer is one place compared to its natural rural background, then we can just multiply this with our heat capacity. So we need to know what our soil is like, and we need to know about soil moisture, and we need to multiply it by a depth, so the amount of soil that we want to extract this heat from, to simply get absolute values of energy that are stored in the underground and that we would be able to extract simply to put the temperatures back at its default levels. We generally call this accumulated waste heat. And what you're seeing here is a paper that is still very much in preparation, where we are trying to do this globally for about 15,000 wells, primarily in Europe and the United States, and a few of them in in Australia, to figure out how much heat is in our underground. And we find, here's the histogram of it, well, it is actually up to 100 megajoule per square meters, which is, of course, first just a number. What is that? Just in comparison, one of these passive houses that kind of are all in and nice and people are getting them, and we all should get them because they're good for the climate. They need about 50 megajoule per square meter per year, so only about 1/4 of what is available in these wells. We also find that this accumulated waste heat increases with the population density at our well location. So we have more energy in wells that are in more densely populated areas, which one kind of leads us to believe that it's probably us humans that led to this heat accumulation, but also in the thought of heat recycling is a good indication that the heat is actually at a place where we need it, because it is at a place where we kind of have a heating demand. Okay, now I want to try and answer the questions where this heat actually comes from. So far I've just told you it is there. Now I want you to understand why this heat accumulated in the underground. And this is very simply due to anthropogenic heat transport processes into the urban underground. This is a study from a couple of years ago, but I still believe it's like one of the best examples, just showing you the different processes. And in fact, there are 5 or 6 of them, depending on whether you count subways, which aren't everywhere available. We have sewage systems, of course, or any sort of tunnels in the underground, district heating networks that will warm your subsurface. You have buildings, you have basements, your buildings are warm. If your building is warm, it will warm the subsurface. And you have the elevated temperatures of the city. So you have your surface urban heat islands that itself kind of just warms the underground. Most of these processes are in fact conductive heat transport processes. So in theory, they are pretty easy to quantify. It's simply, your lambda times the gradient. So your thermal gradient times the thermal conductivity. The difference in temperature from above ground and groundwater temperature, and the distance between those two. Pretty simple if you kind of put it that simple. Of course, though, it is never that simple. In reality, we barely know any of the values we really need to calculate all of this. So instead of just kind of giving exact values, we use a Monte Carlo simulation to determine the heat flux, so to determine the input of the annual heat input in the underground. So that means we are running this analysis not just once, but we are running it 800 times, every time with slightly different parameters. In the following, you're going to see a bunch of box plots, and these box plots simply represent the results of these Monte Carlo simulations, and this is where all of my arrow bars come from. Okay, now ready, we're going to results. Where does this annual heat put in the city mainly stem from? You're seeing this here for 2 towns. You're seeing it in blue for Karlsruhe and in black for Cologne, 2 German cities. And you will hopefully notice that this is pretty big. This one is like the total, so this is just the sum of everything. But here buildings, especially in Karlsruhe, have the highest contribution to all of this. So most of the heat comes from buildings, with the second, or in Cologne actually first, due to elevated land surface temperatures. So we learn that most of the heat that is stored in the underground, most of that waste heat comes from buildings, meaning when we heat our buildings, we are not just heating our buildings, we are also heating the underground. This heat input varies greatly depending on location. So these are just maps of Karlsruhe and Cologne, and you will notice that in some regions it is blue, which in our case means, hey, this heat flux is negative, so actually the subsurface warms the surface. In other cases, it is really red, which means, hey, there's a ton of heat coming from the surface into the underground. These variations are so extreme because they depend on the land cover that is covering the area. I'm now switching countries and looking at a study in Osaka, Japan, because we didn't separate the different land cover classes in the previous study. But what you're seeing here is for multiple years, just comparing buildings, the input from asphalt covered surfaces, the input from bare soil surfaces, and the input from grass surfaces. And you will notice that areas that are covered by grass have a negative heat input, which basically means locations covered by grass show a heat loss. So here the subsurface is losing heat to the surface. So it very much depends on your land cover to figure out how much impact actually your land surface has on the temperatures underground. If we sum all of this up for the entire city and just want to look, okay, now how much energy is there actually in the entire city in the underground? We get this bar. So this is the one on the very right. This is the annual heat input of the two cities I was looking at into the subsurface. This is the amount of energy each year the city loses to the underground. On the very left, on the opposite, we have how much heat is already stored in the underground. This is now how much hotter these cities already are in the underground compared to what they're supposed to be, compared to their rural background temperatures. And in the middle, the most important block, this tells us how much heat we actually use every year for our residential space heating. So this is our annual heating demand. And just from looking at this, you notice, hey, all of these have the same magnitude. And in fact, if we can recycle all of that heat that is already kind of stored in the underground, hey, we can cover our heating demand for multiple years, or at least 1.5 years in the case of Cologne. And even if we just consider our own waste heat every year, so the heat we're literally throwing out of our windows and warming our cities with, when we just reuse that heat, it'll still cover quite a decent amount of our heating demand. In fact, in Karlsruhe, which is like the smaller town of the two and the one with the more shallow groundwater depth, it covers 1/3 of our heating demand. In the last 3 minutes or so, I want to spend one more second moving to Osaka, because here we had the interesting case that we didn't just have one groundwater temperature measurement, but in fact we had two over 2 years for these 12 wells. I forgot how many wells there were. For all of these wells, we have two measurements, one in 2003 and one in 2010. So we had a unique opportunity to actually compare the amount of heat that is actually stored in the underground in this time frame and the amount of heat that we calculated as the annual heat input. So to kind of put it more in an image, which might be easier to understand, we're comparing how much heat the city kind of contributes to the underground in this time period to the amount of heat that is stored during that time. So this would be this red area here, which is just the temperature difference between those 2 years. And well, I must admit, we cannot account for all of that heat that our models show that we lose in the underground. We know that we're losing it. This is kind of clear from buildings models and from our models. But not all of it actually is stored in our underground, in the subsurface. So the big assumption is that either it kind of leaves the city and it goes to rivers and other surface waters, where it then again becomes a problem of groundwater quality, or it simply returns back to the surface where it contributes to our urban warming, which, going back to the beginning of my talk, urban warming at the surface, not a great thing. So I argue the best thing for us to do, and the most best way to deal with this waste heat would be to simply recycling it using shallow geothermal energy system to not just solve our heating demand issue where we so far burn carbon for, but rather also just get rid of the heat that in all the other places only does harm. In conclusion, we've learned today that urban temperatures are warmer than their rural background. This urban heat island phenomenon is not just present at the surface level or in the atmosphere, we also find it in the subsurface. I know some of you studied it in Nanjing as well. We find that groundwater temperatures are actually highest below artificial surfaces. So not just in cities, but also outside of cities, in industry complexes and stuff like this. In fact, we observed that most anomalies we find just happen to be near underground car parks, where they on average are about 5 Kelvin warmer than the background. Quantifying this heat, so we can actually now quantify that buildings are the dominant contributor to the accumulated waste heat in the underground, and that green areas actually release heat from the subsurface to the surface. We cannot account for all energy stored in the underground, but we also know that recycling this heat provides a significant part of our heating demand. And thank you very much. I think I'm out of time.
Thank you so much, Dr. Benz. Well, this topic is quite new and interesting to the audience, I believe, because time is very limited. If you have any questions, please send an email to Dr. Benz. Thank you, Dr. Benz.